Good morning to everyone. I am Sweta from GMRP Gajwel. In this video lesson, I am going to discuss about the working of reflex Klystron oscillator, list the applications of various microwave tubes such as Klystron and magnetron, and explain the working of TWT, that is traveling wave tube, and its applications. Okay, so first let us start the working of reflex Klystron oscillator. Okay, so here this is a reflex Klystron oscillator. So this reflex Klystron oscillator is a low power, low efficiency, single cavity microwave oscillator. So here we are using only single cavity. In the previous class we have discussed multi-cavity Klystron amplifier. In that we are using more than one cavities. In that we use three cavities. One is for input, one for output, and one more is for so here the reflex Klystron is a low power, low efficiency, single cavity microwave oscillator. Okay, so coming to the construction, it consists of a filament surrounded by the cathode. So it consists of a filament that is surrounded by the cathode, and a focusing electrode, that is a negative potential. Focusing electrode, it has a negative potential, and a electron gun. Next, anode cavity, and a repeller electrode. Okay, so it has all these. First one is filament that is surrounded by the cathode. Focusing electrode, it is negative potential. It has a negative potential. Next, electron gun, anode cavity, and a repeller electrode. Okay, so here the electron gun is used to produce the electron beams. Okay, the function of electron gun is it is used to produce the electron beam. This electron beam is accelerated towards the anode cavity. Okay, this electron beam is accelerated towards the anode cavity. Okay, at a positive potential. Okay, next, after passing the gap in the cavity, the electrons travel towards the repeller electrode, which is at a high negative potential. Okay, which has a high negative potential, that is VR. Okay, so the electrons never reach the repeller because of the negative field and are returned back towards the gap. So once see here, the electrons are not reach the repeller, it because of negative field, and are returned back towards the gap. Okay, towards the gap, it the returned back. Okay, under the suitable conditions, the electrons give more energy to the gap to produce the sustained oscillations. Okay, this is about construction, and coming to the operation. So here the electron gun, the construction of reflex Klystron oscillator consists of a filament that is surrounded by the cathode. Okay, tarvata focusing electrode, that is a negative potential, electron gun, anode cavity, repeller electrode. See here, electron gun, filament that is surrounded by the cathode, focusing electrode that has a negative potential, and a repeller electrode, and anode cavity. Okay, so whenever the electron gun, here the electron gun is used to produce the electron beam. This electron beam is accelerated towards the anode cavity. Anode cavity has a high positive potential. It has a high positive potential. After passing the gap in the cavity, the electrons travels towards the repeller electrode, which is at a high negative potential VR. So here the electrons will never reach to this repeller because of the negative field and returns back towards the gap. Okay, so under the suitable conditions, the electrons give more energy to the gap to produce the sustained oscillations. Okay, so coming to the operation. Okay, so sustained oscillations are produced by the reflexed crystal. So by using this Applegate diagram, so first of all, the RF voltage. Okay, so here we are applying voltage. So the RF voltage that is produced across the gap by the cavity oscillations will act on the electron beam to cause the velocity modulation. Okay, here. So the reference electron, here we are considering a reference voltage electron, that is ER that passes through the gap when the gap voltage is 0. Okay, the reference electron ER that passes through the gap when the gap voltage is 0. Okay, whenever ER is unaffected by the voltage. Okay, this moves towards the repeller and gets reflected by the negative voltage on the repeller. It returns and passes through the gap for a second time. Okay, so first we have to consider that the reference voltage ER that passes through the gap when the gap voltage is 0. So here we consider that the gap voltage is 0. This moves towards the repeller and gets reflected by the negative voltage on the repeller. It returns and passes through the gap for a second time. Okay, so the early electron, here we considered reference electron as ER, and the early electron as E. Okay, so that passes through the gap before the reference electron experiences a maximum positive voltage across the gap. Okay, so across the gap, it moves with a greater velocity and penetrates deep into repeller space. So the return time for EE is greater than the ER. Coming to the ER, that is reference electron, the return time for early electron is greater than the reference electron. Next, we have to consider late electron, that is EL. Okay, so the late electron EL that passes through the gap later than the reference electron ER experiences a maximum negative voltage. Okay, so here the return time is shorter as the penetration into the repeller space is less and catches up with the ER and EL electrons, forming a bunch. Okay, so here ER and EL electrons will form a bunch. Okay, the electrons EE, ER and EL forms a bunch. So these bunches transfer the maximum energy to the gap and to get sustained oscillations. Okay, so here transit time. So transit time is nothing but the time taken by the electrons to travel into the repeller space and back to gap. Okay, so repeller space and back to gap. So here to produce the oscillations, it is given by T is equals to n plus 3 by 4. Here T is a transit time, n is an integer. So the practical time, transit time corresponds to a range from 1/3 by 4 to 6/3 by 4 cycles of gap voltages. Next, coming to the applications of reflex klystron. These are used in radar receivers and used in local oscillators in microwave receivers and signal source in microwave generators. And coming to the applications of magnetron, used for industrial heating and used in microwave ovens and used in radar transmitters to produce high power signals. Okay. So these are the applications of reflex klystons. These are the applications of magnetrons. Next, working of traveling wave tube. Okay. So here the traveling wave tube is a high gain, low noise, broadband microwave amplifier. Okay. So here one see, it is a traveling wave tube structure. So it has high gain, low noise, broadband microwave amplifier. Okay. So its operation is based on the interaction between the electron beam and RF field, and both are traveling in the same direction with nearly equal to the velocity of light. Okay. So here the RF field propagates with a velocity equals to the velocity of light, that is Vc. So the interaction between the RF field and the moving of the electron beam will take place when the RF field is reached retarded, that is slow. The RF field is retarded by using a slow wave structure, so that is in a helix. So in traveling wave tubes, when the RF wave and the electron beams are moving with a similar velocities, a continuous interaction between the input wave and the electron beam takes place, resulting in a bunches, and these bunches grow as the beam moves further in the helix. So in this way the input is amplified. So coming to the construction of this traveling wave tube, it consists of a electron gun. Okay. So it produces a narrow constant velocity electron beam. Next one is a magnet. So here it is used to prevent the beam for spreading and to guide it through the center of the helix. Next one is a attenuator. It is used to isolate the input and output waves. To isolate the input and output waves, we use this attenuator. Next one is a helix. It is a loosely wound thin conduction helical wire which acts as a slow wave structure. RF input is applied at one end of the helix and output is taken at the other end of the helix. And collector. So the collector, the function of this collector is it is made positive potential, and as a result beam is attracted to the collector and it acquires a high velocity. Okay. Coming to the operation, that whenever the electron gun produces electron beam is travel through the center of the helix without touching the helix. Okay. So when the applied RF signal, so one see here, when the applied RF signal propagates around the turns of the helix, Around the turns of the helix, it produces an electric field at the center of the helix. The electron beam and RF field both are traveling in the same direction with nearly velocity of the light. Okay, here the electron beam and RF signal input both will travel with the same velocity of the light. The RF field due to the RF signal travel with the velocity of light multiplied by the ratio of helix pitch to helix circumferences. So the interaction here, the interaction takes place between the electron beam and RF field when they are traveling through this helix, and the electron beam delivers the energy to the RF wave onto this helix. Thus, the RF signal wave grows and amplified output. Here, the amplified output is obtained at the output of this TWT. Okay. So, here the phase velocity is equals to Vc into helix pitch by helix circumference. Here Vp is the phase velocity, Vc is the velocity of the light, R is the radius of the helix. Okay, this is amplified output of the TWT. This is a pitch diagram of the helix. And here the applications of TWT are coming to the advantages. Advantages of this TWT is low noise, high bandwidth, high gain, low noise figure, no need of resonant cavities. Coming to the applications, low noise RF amplifier in broadband microwave receivers, repeater amplifier in wideband communication links and coaxial cables, in long distance telephones, and used as output tube in communication satellite, and used in airborne and shipborne pulsed high power radars. Okay, these are the applications of traveling wave tube. So once check all the topics. So first one is a working of reflex klystron oscillator. So here the reflex klystron oscillator is a low power, low efficiency, single cavity microwave oscillator. It consists of a filament that is surrounded by the cathode, focusing electrode, electron gun, anode cavity and a repeller electrode. Okay, so this is the structure of the traveling wave tube. It has only one cavity. So here the electron gun is used to produce the electrons. This electron beam is accelerated towards the anode cavity, that is at a positive potential. It has a positive potential, and after passing the gap into the cavity, the electrons travels towards the. So after passing the gap into the cavity, the electrons will travels towards the repeller electrode, which is at a high negative potential, but the electrons never reach to repeller because of this negative potential, high negative potential field. Because of this high negative potential, the electrons will not reach to the repeller electrode, and this returned back towards the gap. So under these conditions, the electrons give more energy to the gap and to produce the sustained oscillations. Coming to the operation. So these sustained oscillations explained by using this Applegate diagram. By using this Applegate diagram, we'll discuss. So here we consider three electrons: reference electron, early electron, and late electron. So reference electron is passes through the gap when the electron gap voltage is 0, and ER is unaffected by the voltage. So this moves towards the repeller and gets reflected by the negative voltage. So whenever coming to the for early electron, so one see here, electron bunches, repeller space, position of the gap, voltage across the gap. This is an Applegate diagram. And coming to the reference electron, for a reference electron, that reference electron unaffected by the voltage, and this moves to the repeller and returns and passes through the gap for a second time. Okay. Coming to the early electron that passes through the gap before the reference electron experiences maximum positive voltage across the gap. It moves with a greater velocity and penetrates deep into the repeller space. So the return time for E is greater than the ER because here it is penetrating the gap, penetrates the gap. Coming to the late electron. Okay, so here the late electron passes through the gap later than the reference electron, which experience as a maximum negative voltage. Okay, for positive voltage, early electron. So here the return time is shorter as the penetration into the repeller space is less and catches up with ER and EL electrons forming a bunch. Okay, so see here the electrons CE, ER and EL forms a bunch. These bunches transfer the maximum energy gap to get a sustained oscillations. So here the transit time is T is equals to n plus 3 by 4. Transit time is nothing but a time taken by the electrons to travel into the repeller space and back to gap. Coming to the applications. Applications of reflex keystone and magnetrons. Next, working of traveling wave tube and applications. So here the traveling wave tube is a high gain, low noise, broadband microwave amplifier. So it has electron gun, magnet, attenuator, helix and collector. Electron gun is used to produce the narrow constant velocity electron beam. It is used to produce the electron beam, and the magnet is used to prevent the beam from spreading and guide to it through the center of the helix. So, and attenuator is used to isolate the input and output waves. Both input and output waves will be isolated by using this attenuator. Helix is a loosely wound thin conduction helical wire which acts as a slow wave structure. RF input is applied at one end of the helix and the output is taken at this other end. So once here the RF input signal is applied at the one end of the helix and the amplified output will be taken from another end of this helix. Collector is made positive potential and as a result beam is attracted to the collector and acquires a high velocity. And operation, first of all, electron gun will produces the electron beam that is travel through the center of the helix without touching the helix. Without touching the helix, the electron gun will be passes. Electron beam will be passed through the helix. So whenever the applied RF signal is propagates around the turns of the helix, it produces the electric field at the center of the helix. The electron beam and RF field both will traveling at the same velocity of the light. Okay. So here the RF field due to RF signal travel with the velocity of the light that is multiplied by the ratio of the helix pitch and helix circumference. Okay. Once here the phase velocity is equals to velocity of the light into helix pitch and helix circumference. Okay. So the interaction takes place between the electron beam and the RF field when they are traveling through the helix, and the electron beam will delivers the energy to the RF wave. So thus the RF signal wave grows and amplified and output is obtained at the, see here, output will be obtained at the output of the TWT. Okay. Coming to the applications of TWT, see here. Okay. So these applications of TW, it is a low noise RF amplifiers in broadband microwave receivers we use, and repeater amplifiers and used as output tube and used in airborne and shipborne pulsed high power radars. Thank you. Thank you.